Eric, I work for Symbiont, and I have a question for you today. So what do you think is like the best software component? How would you define what is a very, very good software component? I have an answer for you. That's a function, right? And yes, I know how to speak to a room full of Haskell developers because we love functions. But I really mean it. Functions as software components are really great. They have this API where you specify all the parameters you want and the kind of value you want out of the function. And because of it's a functional programming language, when you use Haskell, you have no side effects, so you know exactly what's going on. And then behind the function, there's an implementation doing some stuff, but you don't have to know about it. So that stuff can change, but you just have a contract with that function, right? And that's really good for implementing stuff and changing your implementation. That gives a lot of stability in the software. And functions in Haskell are even better than this, because they can also take other functions as parameters, as if you were passing another component that could be used in the implementation of that function. And they are even greater than this, because some parameters can be abstract. So you can have just type A, and there's not even a UML notation for this to denote an abstract component depending on the type parameter. So the functions in Haskell are really great, and they do all sorts of stuff. And generally, how they implement their behavior is just by, well, calling other functions. And you have like a tree of functions, or more like a graph of functions calling each other to do something useful. And that's all good. But this has one slight disadvantage that I want to put the focus on today. Is that those functions are sealed. And this is actually both good and not so good. So this is very good for encapsulation. That means that you cannot peek into the function if you're a client of the function. You cannot change it. But this is also a drawback, because sometimes we write functions, we know how they are implemented, and we would like to just have almost the same function, but with something slightly different inside. But if the function does not give us the opportunity through its API to change anything, we are done. We cannot change that thing. And if that function comes from a library, it's even harder to change it, just to modify one piece of behavior. So that's really annoying. OK, so let's leave this problem aside for a moment. And I need to tell you a bit about my hobby. So for the past 3 years, when people were asking me, oh, Eric, what is your hobby? What do you do outside of programming? Music, close-up magic. And I said, no, dependency injection. That's my hobby. That's a really crappy hobby. Not one I wish you have. I much prefer doing close-up magic. But that's also a necessary hobby, because when you arrive on a project, you need to know where the code is going to live. You need to know how the code is going to be assembled, how you can replace some parts, how everything is going to evolve. I think that's really important, especially from people that are new to the Haskell ecosystem. They need to know how to build those applications. It's hard if you go beyond just Fibonacci. So when I arrived at Zalando, they were using a form of dependency injection called the cake pattern. And the cake pattern relies heavily on some Scala features as a programming language using traits. So you can mixing traits together. You can have traits extending traits. And those traits, they declare methods that you can override. They can even declare data types that can be exchanged between traits. And they even have this notion of a self-type. That is a way for the type system to declare that one component requires another to do its job. So people thought at the time that this would be a good idea to have like some compile time dependency injection, and that we could build an application like this. But unfortunately, when I arrived in that team, it was really a mess. Everything was blocked. It was hard to write the test. It was hard to refactor the code. All those traits, you didn't know where the functionality was really coming from. It was inherited and overridden in so many places, and then you have name conflicts, and it was really hard. So at that time, I was looking for another solution. Like, can we make all of this just a lot simpler? Maybe by not trying to rely as much on the language, like on the host language. Is there a simpler solution? And I thought, OK, but what's wrong with constructor injection, by the way? So in Scala, you have case classes where you can say, OK, this is my component, and it requires, and I want to have an HTTP client, and it requires a piece of configuration to do its job. I can just inject it in its constructor. And I thought, oh, maybe we could have some form of reader pattern for this, because if I know where to get my thread pool from NA, maybe I know how to build my HTTP client also from that A. I don't need to know right away what that A is. It will be provided later. And then later on, I have a huge piece of configuration having all the right information, the URLs I need, the host, the port, everything. And then, thanks to the Scala implicit machinery, I can build a full tree of those components, where each component declares locally what it needs, and then globally, you have the resolution giving you everything as a tree. And that's nice. You can build a full web server doing all sorts of things with this. But that still doesn't solve all the problems we have with dependency injection. And one of them is that if you get such a tree, some nodes need to be singletons, because some nodes represent, for example, a connection pool for a database. And you cannot allow to have so many connection pools in your application. You really need that resource to be just in one place. So we need effectively to transform this tree into a graph, into a DAG. How do we do this? Well, it turns out that in Scala, there's a nice library to do it called Kiamat, and that library does tree rewriting. And it takes its inspiration from something called Stratego, where you can express lots of strategies to go through some terms and rewrite the trees from bottom up or top down. There are all sorts of nice strategies to rewrite stuff. So I've been using this in Scala to effectively make my singletons. And well, this all works. And this was all put in a library with additional stuff to remove the boilerplate as much as possible. And that was working. But then I moved on from Scala to Haskell. How can I do the same thing in Haskell? And in my case, it was all the more important that I was able to have a nice story for building stuff, for putting components into libraries so that they could be reused across services and so on, and for onboarding new people. And especially the onboarding part was really important because I didn't have very experienced Haskellers with me. I was not even a very experienced Haskeller myself. So I wanted something simple. And I've tried monad transformers and MTL. And I remember just staring at my code for half an hour trying to understand in which order I should put stuff. And that was complicated. I've used the fmonad extensively. I've talked about it. I've implemented the corresponding library in Scala. And something was still not quite satisfying with using effects to create applications. And at that time, I was not really able to pinpoint what was the problem. But I was feeling something was not right. So I tried to look for other alternatives in the Haskell literature. And it turns out that some people have tried different approaches to build applications. And one of them by Jasper, he's here. Yeah, that's his blog post. So another solution is maybe to use modules or define components, not as effects or type classes, but just as records of functions. That's very simple. Create a data type, put all your functions inside. And Jasper is not the only one to do so. There's another blog post called the service pattern doing some very similar things. And this is quite simple, right? This is my API. This is my component, just a bunch of functions. Now, how do I implement it? Well, I need a constructor for it. So I create one of those components, and I provide the implementation for it, right? Here, I'm just putting stuff to the console to do my logging. But the cool thing is that I can create another component that just does nothing. This one does nothing, doesn't print to the console. So I can have different implementations for the same interface. I can have more complex components like authentication. So if I want to authenticate someone, I did something. OK, shouldn't touch. OK, all right. So if I want to authenticate someone, maybe I need the logging component to write some logs to the console while I'm trying to authenticate someone. So I can, in my constructor, require that component as a dependency. And maybe I need also a piece of config to do my authentication. So I have constructors taking several parameters to build components. That's quite simple, just functions. But then, OK, how could I reuse this reader machinery that I've been using in Scala and the tree rewriting? Actually, no, because the tree rewriting stuff in Scala is using lots of reflection to go through a tree of Scala values and rewrite the pointers to the right place and so on. I didn't know how to do this in Haskell. So maybe I needed to change my approach. So instead of building something and then trying to tweak it, maybe I could just try to build it so that it had just the right shape. So maybe I can specify what I want, and some kind of algorithm is going to build the right thing for me. So I tried to think about, OK, how can I solve this singleton problem first? And maybe I can solve it by having just two type classes, right? So if I want to make something that's the make type class, OK, I can make something out of some state. And that state comes from a registry where This is a place where every time I make something, I just register it. So if I need it to make other things, I can just retrieve it right away. I don't have to rebuild it. It's like having a cache for your components. And by using those two type classes, I can have some instance of those type classes, say, okay, my authentication, how can I make an authentication component? Well, I can make it if I know how to make the config, if I know how to make the logging, and then if I can register the component I just made somewhere so that it can be accessed later on. And that will make all singletons in my application graph. And then the implementation of this instance is very boilerplatey, because what I just said is almost always the same. It just changes a bit with the arity of your constructor. So I created a bunch of helper methods like create 1, create 2, 3, 4, and whatever. I didn't really know how to abstract over this arity of each constructor. But at least I had somehow a working solution. The other annoying thing is that there's a bit of duplication here, because in my new function, declaring all the dependency to create something, I already have those dependencies. And then I have to repeat them in my instance. That's quite ugly, right? So that it's not very practical. Every time I add a new dependency, there are more places in my code where I need to change stuff. I need to go create 3. And then I need to add one more constraint in my instance. So that's not so nice in terms of refactoring and being able to evolve the application. But there was, and that's how the registry is implemented. So I used like 2 lists of almost 2 H lists where some parameters were optional, some parameters were mandatory as my cache. As I was building components, I was putting that stuff in a registry. And then this is the config. So you put all the leaves in your graph somewhere, like the URLs, the credentials, where to get all those stuff. You can create this registry for production, the same registry for your staging environment, for your development. And then depending which base information you take to build your application, you will get different things constructed. But then there was a showstopper, like a big one, which is most of the time I want singletons in my application graph. But sometimes I don't want singletons. Sometimes I want the exact opposite. Sometimes I want some components of the same type to be configured differently. So if I have 2 listeners that have the same type listening to some events on some Kafka bus or whatever, they need to be configured with different event types, with different topic names. How do I do this if everything is merged into one node? In that case, in different contexts, I want a slightly different configuration. That was a real showstopper, because with this type-directed resolution, I can only have 1 value per type. That's really annoying. So, what can I do? It's, when you reach those roadblocks, it's really sometimes really, really frustrating. I don't know how to abstract over the arities. I don't know how to deal with duplication. And then this big thing about how do I do contextual configuration. So a colleague of mine, Simon, tried even more crazy stuff using the type system, using type families, and tried to even describe the full graph with types. What does that mean to have the full graph with types? And you have lots of type families, and it actually kind of works, which is quite impressive, I must say. But I was thinking I was getting further away from my original goal, which was to have something really simple that I could really explain to newcomers, people that were new to Haskell. That was not doing it. So back to the drawing board. What can we do? And actually, there's a very simple idea. Let's have a look at it. This registry thing where we put stuff after we build those things. So what if not only we put stuff when we build those things to just like kind of memorize them, but what if we also put the constructors inside the registry? And now let's say I want to build an authentication component. So what do? Well, I go through the list like top to down, and I see, oh, there's a function building it. That's nice. Can I use it? Well, I can use it if I know how to make the inputs for that function. Do I have those inputs in the list? Well, I go down and I see, oh, yeah, I have one for the config, and I have one for the logging. So then I can invoke my function, and I can get my component. Once I've made it, I just put it on top of the list, and then it's available for any other constructor that needs to do some authentication. And that's a very simple algorithm. It's a simple data structure and a simple algorithm. And this is all in a library called registry. So that's the thing I want to really present today. So before we see how it works to build a full application, let's see another example on how we can use this registry to assemble functions to do useful things for us. So let's say you want to encode a data structure that's kind of a tree in JSON, right? So you have a company, having departments, having employees, name and age for each employee. So what do? Well, okay, you encode the name and age using string and number as JSON primitives. And then at each level of your model, of your data structure, you create some new encoders, right? So for example, the company encoder requires a department encoder, and you call that, and you have those functions calling each other. And then you put this in a library, good job. You can give it to someone. Now you know how to encode a company. That's nice. But then I receive this library and I say, what did you do with your employee encoder? The field names, they are really bad. It should be name and age, not N and A. That's really crap. So what can I do with this? Actually, I cannot do much at this stage. I have to rewrite everything. Because if I have a company encoder, I cannot really change my employee encoder right away. So let's take a different approach. Let's now parameterize everything. So now you have your company encoder function taking a department encoder, and the department encoder taking employee encoder, and so on. So that's good, because then now it's possible, given all those functions, to have the right behavior and change the employee encoder if you don't like it. But it comes with a price of having lots more boilerplates. So now to have just a company encoder, you need to write an expression where you say company encoder of a department encoder of an employee. That's a long expression. That's very tedious to have to assemble those functions manually. So why not put them in a registry? So let's do this. So you put them in the registry and you say, can you please make me a company encoder? And it will go through this algorithm of saying, OK, I have a function to build a company encoder. What does it need? A department encoder. I have a function building this. And recursively, it's going to build everything. And you can just say, OK, make me an encoder for a company out of the registry. And because of the way the algorithm works, now it's also very easy, given a base registry, to slightly alter its behavior. So if you want a better employer encoder to be used, well, you can just put it on top of the registry. And that's the one that's going to be taken, and that's going to be propagated everywhere it's needed. So that gives you a very easy way to replace any value that's being called anywhere in a function call, a function graph, or in an application. So now if you think about this, about how do I mock my application, you have a large application with lots of dependencies. You say, now I want my logging to be done, to this file instead, or no logging at all. You just put no logging on top of your registry, and you ask to rebuild all your application again. And that's done. You have a very easy way to mock every dependency, even if they are very deeply nested in your graph. It's almost too simple. But it's actually not that simple when we build applications. There are more things we want when we build applications, because those components generally, they instantiate some resources, so we need to deal with some effects. We want to make sure that all this construction is safe. I'm going to talk about it. We also want to show what's in the registry. So can we even, at this application startup, show what's inside the registry to make sure we haven't made any mistake with our configuration? So let's talk a bit about how it's implemented. So it relies on two type classes and one data structure in Haskell. So everything you put in the registry is inserted as a dynamic value, right? It's a way to say, I don't really care about the types, I just trust you. And the values, the things you put inside the registry are of two types. Some of them, they all need to be typable, but some of them are also showable. You can also show them, like a piece of configuration, like a host or port, you can show it. And otherwise, the constructors, you just require them to be typable, right? To put them in the registry. That gives us already one nice feature, which is you can create a registry with some values with one constructor and open JSCI and see what's inside the registry. So you have the values, you have their types, and you have the list of all the constructors inside your registry. But actually, you can do more, because with even not starting your application, you can also extract all the dependency graph of your application and create a dot file. So this is the representation of one of our services, and as a dot file, because you resolve all the dependencies, and you can print out how it's configured. And here we can see that logging is indeed a singleton being used everywhere. And it's the same for the connection pool. That's good. That's exactly what we want. But some of you might be very afraid because I said dynamic, and we're not supposed to, it's not a dynamically typed language, right? And is all of this really safe? If I put dynamic values somewhere and now I want to extract them, is all of this going to be safe? So actually the make function contains a few guarantees about the safety of all of this. So first of all, if you want to extract something out of the registry, you need that thing to be typable. We need to be able to access its type because we need the type to see where it is. Then the registry itself contains two lists of types. The last one, the out part, is a list of all the outputs of all the functions and all the values. And the ins part is the list of all the inputs of all the functions, right? So if I want to extract something out of the registry, I must at least check that my type A is in the list of all the outputs. If it's not in the list of all the outputs, I know that I will never be able to build something like this. But there are more complex conditions, right? I also need, and this is encoded in the solvable constraint, I also need to make sure that I will be able to build all my inputs. So I have a constraint saying that the list of all the inputs must be a subset of the list of all the outputs to make sure that I will be able to recursively find them. The only thing that's not encoded in that yet, in that solvable type class, is what if I have cycles in my graph? What if I put int to text and text to int in my registry? It's going to cycle forever. That's really bad. So at the moment, this is not type checked, but this is runtime checked. And the way it's runtime checked is by maintaining a stack. So every time you want to build something, you put it on a stack. If it has some dependencies, you put all the dependencies in the stack. And if at some stage you realize that you want to build something that was already on the stack, you know you have a cycle. And actually, as we'll see, this stack is useful, and we will use it for something else. But then at runtime, you will have an exception saying, oh, sorry, here you have a cycle in your components, which actually should not happen very often. Because if you start building an application where conceptually your components have cyclic dependencies between themselves, it's really bad. And generally, if you put them in different files, I think that GHC will also tell you, by the way, you have cyclic dependencies between your modules. So that should not happen. So yeah, this is not yet encoded in the type system, but I also don't think this is such a huge problem. OK, and then I have some very practical concerns. I mean, we need to be very practical sometimes. And compilation times are a very practical concern. And I've tried this thing with like a registry of almost 100 elements. So in that case, I don't also want to have huge compilation times when I know that everything is working OK. So there are different versions of that make function that remove some of those constraints if you realize that things are getting a bit slow in terms of compilation times. So you have make fast and even make and save. Well, you can also trust yourself in the test, for example, that you're doing the right thing and go make and save, and then you have less compilation times because less things will be checked. You will get an exception, but the exception will be actually quite informative. It will tell you what's in the registry, what you were trying to build, what was not found, and so on and so forth. So it's maybe even better than a type error that might be quite cryptic sometimes. OK, so now let's talk a bit about FX, because building applications, most of the time you don't have pure components when you build applications, because your components, if they access a database, if they do some logging, sometimes like there's a library doing some logging that's just caching the dates to be faster, and that's good. But then that means that component needs to be in I/O. It starts, when you start it, it does some I/O action. Other components, like you want to maybe encapsulate EKG, like the metrics library, inside a component and give access to that library. That thing is going to also start something. So creating that component will have an effect in I/O, right? And some of them are just pure functions. Like the constructors for those components are just pure functions, and it's all fine. But now if you put all those constructors into the registry, the types do not really align. Because if I want to make my authentication component, it requires just a logging parameter, input value. But what I'm going to have is an I/O of logging. So there's going to be a mismatch here. So how can we solve this? Well, the solution I found, which I think is quite practical, is to lift everything to the monad you are eventually going to use for starting up everything, right? So there are different keywords to do this. So you can lift a value to a given monad, lift a pure function to that monad, or sometimes lift just the arguments of the function to that monad. And then everything will be aligned, all requiring I/O values. And this is the kind of registry you will find for a real application where we are really doing stuff, we are really starting stuff. But unfortunately, that still doesn't really solve the problem of the singleton. And you know, again, that's one of the steps where you think, oh, I nailed it, and then, oh no, I haven't. Because if you start a database using an I/O of something, of a database, what you get is an action that's going to start the database. But if you use that same action into two different functions, well, you're going to start the database twice. So what we really want here is to memorize this action of starting a database. So there's some additional facility in the library to create real singletons in that sense by doing a bit of caching. So the singleton function says, OK, if you get something looking like I/O of database, please cache it. And the whole thing then, creating the registry itself, becomes an I/O action because we have some cache going on here. So it's not, creating the registry itself is not a pure action anymore. It seems more complicated that we are adding like new val2, fun2, singleton, and so on. But it also leaves the main resolution algorithm very simple. That one doesn't change. It's all type directed. The types are all the same. They just need to align. That makes things very simple in terms of resolution. Oh, OK, so now how are we going to solve this problem about having two different configurations for two different components of the same type in the same app, right? You remember this thing? Because we are still making singletons by putting everything we build on top of the registry and then reusing them. Oh, actually, we have a way to solve this problem. Because I told you, when we try to detect cyclic part of the graph, I keep a stack of everything. So the stack can be used. It gives us more information about what are we trying to build right now. So we can just reuse this information and specify that, OK, if I'm trying to build a products consumer at this stage, if you need a listener config for anything, just use that one. And that's the one that's going to be taken. And then if I'm in a different context, building a partners consumer, then you can use another piece of configuration. So we have a way to intercept all this creation and the context in which we want to create something to do the exact configuration we want. And this is really great because that means now this listener component, we can really put it in a library somewhere with no fear that we can reuse it without ever having to change that code or new type something or do some trickery to just make it do what we want to do, because it will do what we want to do. We don't have to pre-wire that thing in advance. OK, so if you look at the library, you will see some additional support for dealing with those resources. In particular, when you start stuff, it's nice, but you need to shut them down gracefully, like connection pools and so on. Let's say you're on GHCI, you start something. You also want, after you've done something, your resource to be closed. Otherwise, the next time it will not work. So there is an RIO type, which is basically a resource T of IO doing this, but it does a bit more. So it also does some checks on startup. So you can, on startup, preload your caches, for example. Check that you have the right configuration. You can add additional checks. And then it will give you a result back. And if that result is positive, you can run the next action. So there is additional support for building real applications. So as far as I'm concerned, this solves all my problems with dependency injection without requiring anything fancy in the type system. No effects, no higher order, no for all function, no natural transformations of any sort. I'm really satisfied with this because that solved all my problems, and I know I can explain this to someone that's really new to Haskell, and because it's just basic data types, a basic data structure, and an algorithm associated to it. But the cool thing is that it's not limited to building applications, because the problem we are solving here is assembling functions. And there are other situations where we want to assemble functions. So one of them is encoders, but there's another one is data generation with not quick check, but hedgehog. So who knows about quick check first? Yay. And hedgehog. So hedgehog is like a variation on quick check, where the people who created the library decided to get rid of the arbitrary type class. And the reason why they decided to get rid of the arbitrary type class was that with type class resolution, you have one instance per type class. So I have one arbitrary company. I can only have one instance of this. But when you write tests, you want to have many different instances of your arbitrary company because there are many different contexts that you want to test. So that type class most of the time is not as flexible as we would like it to be. And people writing the Hedgehog library, they said, oh, let's forget about type classes. Let's just have generators and manipulate them as we wish. But then let's think about the constructors for the data model that we have, like company, department, and so on. Those constructors can also be lifted to be constructors on generators. Like a generator for a company can be a constructor for, can have a constructor using a generator of an employee and a generator of a department, or just a department, and then to create a generator of a company. So we can also put all of this in a registry and say, hey, can you please make me a company? And we will go through all the functions for creating generators and create a new one. And there's a really cool aspect to this, is that every time you evolve your data model, every time you change something, you restructure stuff, you don't have to change anything. Because all we put in the registry here are the constructor names. We don't specify what parameters they take. So if you add a new parameter, it's not a problem. You don't have to change that code. So it's very, very refactor resistant, which is a quality which I'm really after when I want to evolve an application and restructure it easily. I don't want to have to change so many code in so many places. But you can also do more because you have, in your data model, you have relationships. So you have things saying, okay, I have a maybe relationship with something else. So that's also a constructor, right, for creating maybe relationships. And you can specify that by default, all your lists relationships will have from 0 to 3 elements. And you put this into your registry, or non-empty lists. And then if you want to have a different behavior for lists, you can add a different generator for lists on top of your registry. You will get a different one. And we can push this idea even further. So I just said if you want a different behavior, you put something on top of your registry, meaning that I can modify my registry, right? I can write a function that takes one registry and returns one where I'm going to have a slightly different behavior. So I can say something, oh, now I want to have just one employee in my company. So how do I do this? Well, I can just say every time you generate a list of employees, just take the first one. And that's going to modify my registry. And that's a function from registry to registry. And I can do the same thing for a department. I can now say, every time you generate a department, just put one. And that means that those things are just functions from registry to registry, meaning that I can compose them. And I can say, okay, that's a minimal company for me. Just one employee, one department. And it's very compositional, right? You just add functions on top of each other. You don't have to modify any code. Just by composing transformations on your state, on your registry, you get the behavior you want. You don't have to change anything. And you can push with Hedgehog this idea even further. So in Hedgehog, you have properties like you have in QuickCheck, but those are, they have a transformer for it. There's a property T, meaning that you can add more effects into that property T. In particular, you can have a state effect. And you can choose to have a state, your registry as state. And you can say, oh, now you can have functions that are just going to modify the state of your registry and insert them in your property, in your do comprehension. And you can say, can you please make sure that in my list of all the medias, I have one media at least in my list, and it must be well-formed. So this is all in the context of the work I was doing at Zalando, where it's a web store for clothes. And the data model is structured into different levels, where you have the model, what it is to have a t-shirt, and then you have different configurations for the different colors, and each configuration has different sizes, right? So it's like a tree, like this. And what we want is some flexibility in generating different trees, having different properties. And here I'm saying I want at least to have one image that's correct at each of the configuration level. And you can also say, oh, I want to replace one generator for the size of the media, because what we check that the size of the picture is correct. And we say, okay, what would happen if the size was incorrect? So I can just inject, just with one line. I don't have to modify anything else. I can inject that behavior. And then the second line, building all the model, is going to use that generator that I just replaced with an invalid media to create a model that will have an invalid media. And I didn't have to change any of my arbitraries, any of my generators to do this. It's just based on state transformations of my registry. There was another option that was taken and that you might think of when you try to generate data is, okay, let's generate the right thing and then tweak it. It's like the build and tweak approach I was mentioning before. And you can do this using lenses, for example. But there is also one drawback with this, is that this path expression that you use for your lens is not very refactor friendly. If you decide to change your data model somewhere, you will have to go everywhere that you have a very precise path expression and change it to use like possibly different combinators. So that makes all your test code quite fragile if you try to use this approach. So as a conclusion, I think functions are really great in Haskell because they provide us lots of functionality, they provide us good encapsulation, and that's absolutely necessary when we build software. But unfortunately, there's lots of like associated boilerplate of just working with functions. And we are trying to find so many different ways to deal with this. And most of the time, the thing we reach for is type class and type class resolution, because it's like the most obvious thing of having like an implicit wiring done for us. Unfortunately, type class resolution was not really made for building applications. It is quite inflexible. That's not what it was made for. But why not extract it? Why not represent it? Why not create an algorithm doing almost the same thing, but just more practically, just with all the bells and whistles that we need to just tweak it as we wish. So then we can program with functions all the way down. And please explore the library and tell me what you think. Cool. That's it. What time is it? So yeah, there can be questions, and I have 2 additional slides because we're really early, so I can go bonus slides. Because maybe you all have this question. Why not MTL? Why not F, right? And I want to try to give a short answer to those questions, because we see many blog posts advocating MTL and using deriving via to make things less boilerplatey and so on. I think that we have several problems. So one of them is encapsulation. So every time I write a function like this, I'm really breaking encapsulation. I'm saying, okay, I can authenticate a user provided that you give me this capability. But that should not be your concern, how I choose to authenticate a user. That makes you very fragile, very dependent on how I choose to do things. If I choose to do things differently, you have to bubble up other dependencies on how I am doing things. So I think that's not the right approach because of this essential problem. And then everything that's type-driven has this issue with specialization where we want to try to instantiate different things, I mean, the same type with different values. And this is something that's hard to solve with type classes, especially when those things are like deeply nested. Now, the other issue is with F, and I think I was able to finally pinpoint my issue with F, is that when you create effects, they are really nice. It's really easy to use those effects and require something and you just use those effects. But unfortunately, your interpreters, how you call them, they start having dependencies between each other when you start having different layers in your software. And those are just function calls, those interpreters calling other interpreters and so on. So they suffer from the same issue of being very opaque. And the top-level interpreter, if you want to tweak something and do something slightly differently, you have to open it up and pass another interpreter as a parameter and so on. And write all sorts of ad hoc interpreters calling each other. So that's quite annoying. OK, now I'm open for questions. And maybe the same questions I can... Yes, Oscar.
Yeah, so with like MTL and maybe F, I haven't used that so much, but I see it as partly sort of dependency, being able to declare dependencies for some function, but also being able to swap effects. Have you done anything like that with your registry thing? So you were using I/O in your examples. Can you have components that can swap the effects for like running them in a test with a pure like identity instead of I/O?
Yeah. So when I started, I deliberately took I/O as my almost I/O, something slightly different, as my interface for all the components. For one reason was that I wanted easy interoperability between everything. And I wanted to be able to put my components, because I/O is like the least amount of requirement you can have on something, right? It says, I'm having some effect. You don't know what, okay? But that being said, you have lots of flexibility here. So you don't have to use I/O. And there are even some cases where I/O is not cutting it, because if you want to pass something like a request ID, you need some form of reader here. You cannot encode a request ID passing with just a component doing it. So you generally need more than I/O to do this. But you could think of using unexceptional I/O as your API, for example, for those components, where you say, I'm having some effect, you don't know what, and that's for your own good, because you don't want to depend on my implementation, but I can at least guarantee that you will not get any exception. So I think the design space is still open about how you express your API for each function. Yes?
So for the example of the generators.
Yes.
Sorry, for the example of the generators, is this on? Okay. Can you hear me now?
Yes.
The generators. So it was like one registry for your generators, right? But if I'm writing generators, one thing I want is to use generics to generate the generators. For a record, for example.
Yep.
So is it possible to do that with the registry? It looked like you kind of had to explicitly, for a record, you had to explicitly say how to construct it.
You also have to explicitly say deriving generics everywhere you want to have your generation. No?
Yeah, but I don't have to say, like, if I've got a record with like 10 fields, I don't have to explicitly create a constructor for that.
But that's the same situation. You don't have what do you mean by record with 10? If you have a data type with a constructor for that data type, you put it in your registry, whether it has 2 or 10 fields.
And it'll work it out.
Huh?
And the registry will be able to work out.
This is just a function, but that function is lifted to gen. So we can take a function that has pure arguments, like a constructor, and lift it to an applicative context. And that's what the fun at gen is doing. It's lifting the whole function to arguments being generators themselves. It's essentially writing down for you the bracket dollar, arbitrary bracket star bracket and so on.
Okay, just think about this.
Yeah. It's quite nice actually. So please choose whoever or you.
First, I love this. I'll need to get that out. But I have an example where components have typically type A to A with the same A, or a monadic version of that. So it gets a bit outside of your sort of programming model there, because you should have just one function per type, I think.
Yep.
But is there something I can do to integrate? Like maybe the tweak thing that you showed earlier could help?
Possibly, but it's interesting. You have a component whose type is A to A. What's that situation? I want to talk to you about this.
Transformers, they change some sort of I/O into another sort of I/O, and they have the same interface.
But is it the type? I mean, the components generally are just a bunch of functions. Yeah. So your function might have inside a component, that can be your API from A to A, but the component is just a list of functions.
So it's the component is a list of function, but it takes the same functions and return the same functions again. And it's actually useful for mocking and for testing things separately.
Let's write it down together because okay.
So your components are a list of functions. So I'm interested in how the specialize is working, because you're saying, I want to specialize this to a particular instance.
Yep.
But then you're presumably trying to do some equality on that list of components. So
we're always using like type equality to know what we want to build and which types we want. So as I said, when I'm trying to build something, I'm maintaining a stack of my context. So I was trying to build my app. To build my app, I need a products consumer. To build a products consumer, I need some logging, and then I need some event listener. Okay. So I have this context somewhere. And then I have a list inside the registry saying, oh, there might be some things you want to specialize. So if you are in that context, if in that list there's one of these types, then you know that if you want to build a listener config, use this value, this exact value. Don't try to fetch it from anywhere else. So that's the algorithm, if you want.
It may be rarely the case, but you move from type class resolution to runtime resolution. Doesn't it harm the performance since you don't have JIT?
Yep. So, I mean, it's a good question, but it's also something that we do generally only once when you build the application. So you start your application, you wire all your components, and then you just use them as a bunch of functions calling each other. So after you've started the application, the registry is not used anymore. It's not supposed to be used on the fly for everything you do. So I don't think that harms performance in that sense. Yes, only to wire things up, and then you can use them. All done. Thank you.